Was that the water? Okay.
Yes.
Sorry, no, was that 2 and O2?
So we're looking at H2O liquid goes to H2O gas.
Oh, sorry, no, it was the one after that.
We're looking at number 77.
Oh, N2 and O2. Okay.
Yeah, we did that one.
Let's do that one. So this N2 gas plus O2 gas, number 77, is going to produce 2NO gas. And we look at the delta G. What was the delta G under standard conditions?
173.
Plus 173. When you see a number that, is that big or? Yes. When you see a number that big, it pretty much tells you that there's pretty much no reaction. I mean, that's a pretty big positive number. Highly non-spontaneous, right. And it's a good thing because NO is toxic, but just it's a big number. In fact, the typical range we look at, is between, what number should you remember from delta G? Yeah, plus 50 to minus 50. Anything beyond that is pretty much one way or the other. And so this is highly non-spontaneous, but maybe we can make this spontaneous. And so we want to do all the things, Well, one of the things that could make this spontaneous is by changing the temperature. It might work, it might not work. Another thing would be changing the pressure or the concentration, right? In other words, going non-spontaneous. We could go non-spontaneous at 298, or we could go non-spontaneous at an alternate temperature. And so basic strategies of making something like this, which is highly non-spontaneous, into something that's potentially spontaneous, is to, 1, try changing the temperature. 2, if that doesn't work, try maybe changing the pressures. In this case, these are gases, so we could change the pressure. If these were solutions, we change the concentrations and maintain the same temperature. Or 3, a combination of the two. And so first off, let's see the temperature, if it's even feasible with temperature. And so the first thing we'd look at is delta H, And if I look at this, under standard conditions, you know what this reaction's called? This reaction's called a formation reaction because we're forming the compound from the elements in their standard states under these conditions. Except, it's not quite a formation reaction. What's the difference between this reaction and a formation reaction? Formation reactions are per mole. We're forming 2 moles here. And so what we have to do is, this is 2 times delta H of formation of NO gas. I mean, if we're going to form twice as much, it's going to cost you twice as much energy, or produce twice as much energy, depending if it's exothermic or endothermic, right? And so energy is extensive, so twice as much energy. And so what is the delta H of formation of NO gas? And does somebody have Appendix D handy?
It's in our books.
Huh?
It's Appendix D in our books.
Yeah, at the end of the book. Otherwise, I'll go get mine. The other thing we could do is delta H of reactions equal to the sum of the delta H's of formation of the product minus the sum of the delta H's of formation of the reactants. But when you look at the reactants, to form N2 from N2 gas is going to cost you 0 energy because no change. The same thing with O2. The delta H's of formation of the elements in their stable state is 0. And so, if we did it, this would be minus 0, this is 0. Oh, Vincent, did you find?
I'm still looking for it.
Look under nitrogen.
Actually,
Appendix D, delta H of formation.
NO2.
NO.
And, oh yeah, it's plus 90.29.
plus 90.25 kilojoules.
Yeah.
That's for 2 moles. Or is that for 1 mole? That's for 1 mole, so we have to multiply by 2. 180.5 kilojoules. And so that's endothermic. Endothermic is not favorable reaction. And it's, yeah, pretty positive here. Let's take a look at delta S. Delta S naught will be the entropy of the products minus the entropy of the reactants. All right, Vincent, since you're on NO, look, what is the absolute entropy of NO? No, S. S. Not delta S, just S. And so it's going to be 2 times the entropy of NO, gas, products, minus reactants, minus the entropy of N2 gas plus the entropy of O2 gas. We have to double the NO because we have twice as many moles, so what does it come out to?
The S for NO is 210.8.
2 times 210.8.
Yeah.
Units here would be joules per Kelvin. And then what is the entropy for N2?
2 is 191.6.
191.6. We only have 1 mole of that, joules per Kelvin. Gases should be like 100 to 200. Yeah, except we're going to do this as written, as this reaction is written. And so we see, yeah, it's per mole, per 2 moles. And so the moles will cancel out. That's what this is, 2 moles, the moles cancel out. There should be 1 mole, the moles cancel out, and this is going to be 1 mole. And so O2 is going to be what? 161.1.
Oh, O2? Oh, sorry, that's 205.1.
205.1. All right, so this entropy is going to come out to, is it? $23.9. What do you guys get? $24.9. All right, thank you. Joule per Kelvin. So what we have is we have the enthalpy going up and the enthalpy. And so if we go back here, you know, delta G is equal to delta H minus T delta F. If the enthalpy is going up and the entropy is going up, then this is not favorable, this is favorable. So we can make this favorable term bigger by adjusting the temperature. By increasing the temperature, we can make this reaction more spontaneous, if not totally spontaneous. So here we call this non-spontaneous at low temperature, but spontaneous at high temperature. And so this is possible to adjust the temperature. What we want to do is we want to increase the temperature to make it spontaneous, because the delta H term is preventing this reaction from occurring. The delta H term is kind of big, 180.5 kilojoules. And so what we have to do is we have to pick a temperature so that the entropy term will at least cancel this out or make this whole thing negative. And so this is going to be 0.0249 kilojoules per Kelvin.
And so what they're going to do is increase the temperature, make this term bigger, and eventually cancel out this term. And continue to make this term bigger to make this whole thing negative. And so in order to cancel out the positive 180.5, I need a negative 180.5. And so in other words, I got to figure out what temperature will this turn into 180.5. And so doing that, there are different things I could do. I could just do it off this, or I could just set delta G equal to 0. I want the positive term to be canceled out by the negative term. So delta G equals 0, which is equal to delta H. This is under standard conditions, minus T delta S under standard conditions. And then solve for the temperature. The temperature is equal to delta H over delta S. Okay, this is going to tell me what temperature this whole thing will turn negative 180.5. And so the delta H value is 180. I'll just write this in joules. I did it in kilojoules here. We'll do it in joules down here. 180,500 joules. Delta S is 24.9 joules per Kelvin, which gives us a temperature of what? 400, what is it? 725 Kelvin. So if I plug in 725 here, then 725 times 0.0249 should be 180.5. Is it? Yes? Yeah. What?
I got it. It's 7,240.
7,000? 7,249. Okay, sorry, I misheard you. 7,249 Kelvin. And so if I put this temperature here, then it'll exactly cancel this out. This is preventing reaction. And so what I need to do is I need to have a temperature greater than this, right? In order to get this reaction to go, I need the whole thing to become negative, not just cancel out. And so the temperature should be greater than 7,249 Kelvin. And then this reaction should become spontaneous. Is that an easy temperature to achieve? No. 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 Yeah. Even in a volcano, that's going to be a tough temperature to get. The temperature like that is going to vaporize everything. It seems. And so this is going to be a tough temperature to get. So raising temperature will be difficult. And so we got to think, what else could favor this? Yeah, the other alternatives would be to change the pressures, because under standard conditions, what are the pressures? Here. 1 bar. O2 is 1 bar, and NO, 2 bars? 2 bars or 1 bar?
1 bar.
1 bar. But why is there 2 here? Because there are 2 ways to visualize a gas mixture. Are you guys familiar with the 2 ways? This is something I talk about in Chem 1A a lot, but I'm not sure if they talk about it in your Chem 1A very much. Chem 4 is probably better described. So we have a box of nitrogen this big. The box of oxygen is going to be the same size. Both of these are at the same pressure. The box of NO will be twice this size. And so the 2 comes in, well, it's going to be twice as big. But the pressure is going to be the same. And so if we were to combine all these, let's say this is 1 liter, 1 liter, and 2 liters, then the total volume would be 4 liters. because the pressure can't increase. Does that make sense? This is called the Daltons, or Avogadro, not Daltons, this is called Avogadros. Oftentimes we think in terms of Daltons. In terms of Daltons, you know, the gases occupy the same volume. And so what's different is the pressure of the gases. But anyway, we'll talk about this. This is going to be hard to achieve. Therefore, what we probably should do is try to fiddle around with going non-standard conditions and see. But even though, you know, in theory we should be able to make this spontaneous, in actual practice this is going to be impossible, right, to achieve that kind of temperature. Unless it's some kind of plasma or something like that. All right, the next, but then we'd have other reactions that could potentially occur as well. Next, try non-standard conditions at RT. Next, try non-standard conditions at T. And so, you know, we try to play around some more with this. But what we're going to do is we're going to leave this because I'm going to do another sample problem where we're going to do something similar to this. And we're going to look at the problem itself. Number 77 says an equimolar mixture of N2 and O2 equimolar mix of N2 and O2 and so equimolar mix is allowed to react and they're asking at what temperature will 1% of the mix be reacted. And so here we're going to just set up an ice table. What we want is we want 1% reaction to occur and then stop. Therefore, at equilibrium, we should have a case where 99% of the nitrogen or 99% of the oxygen remains unreacted. And so what is the initial pressure of N2? Do they give it to us? They don't. And so we have two choices here. Choice one, we just pick a pressure. Since they didn't give it to us, we could say N2 is at 1 bar, O2 is at 1 bar since it's equimolar. Or if you don't like doing that, you could just say, well, N2 is going to have some initial concentration. Or not, actually, sorry, initial pressure. N2 is going to have initial pressure. These are gases. O2 is going to have initial pressure. And the initial pressure of N2 and the initial pressure of O2 should be the same. What is the initial pressure of NO? There's no NO in there, so it's 0. Okay, now we want 1% reaction, so how much is the change going to be? Yeah, the change is going to be minus 0.01 of our initial. And I'm just going to call it PI because they're both the same. So this would be minus 0.01 P initial. And therefore at equilibrium, I'm going to get P yeah, in other words, I could just do this. 1 minus 0.01 gives me 0.99 P initial, so 99% remains, right? And 0.99 P initial. And over here, this is going to be plus actually O2 P initial, because we form twice as much. And so
Down here, we'll get 0.02 P initial. We want it to stop here. And so what this is going to do is it's going to fix the equilibrium constant. That is, if we want the reaction to stop here, then this is going to have to be the equilibrium partial pressures that will result from this. And so the equilibrium constant here is going to equal the pressure of the NO squared divided by the pressure of the N2 times the pressure of the O2. The pressure of the NO squared is just 0.02 times PI, quantity squared. And then N2 and O2 are the same, so this is going to be 0.99 times PI squared. PI cancels. And so what does K come out to?
.08 times 10 to the negative 4.
So if the equilibrium constant were 4.08 times 10 to the negative 4, what we'd get is we get 1% reaction, and then we'd stop here. This would be the equilibrium conditions. And the thing about K is we can change K with temperature, just like we can change delta G with temperature. All right, now at what temperature will K have this value? And so that's the question. At what temperature will K equal 4.08 times 10 to the negative 4? And so we go back through our equations and we look, delta G is equal to delta G naught plus RT ln a Q. We have this one. We have delta G naught is equal to minus RT ln of K. Well, this looks like the right equation. So we'll solve this one for T. T is equal to delta G naught divided by minus R ln of K. And so all I have to do is plug in my delta G naught. What was the delta G naught we had earlier? Plus 173, was it?
Yeah.
All right. But this whole thing is going to be negative. So it's a negative times a plus 173. Will give me negative 173 kilojoules. R I could just convert it into joules. I mean kilojoules, which would be 0.08 to, what is it, 8.3145? So 83145 kilojoules per Kelvin. ln a K. Well, I know the K value that I want. The K value is 4.08 times 10 to the minus 4. And then I solve for the temperature.
So why did we change the delta G to a negative again?
Oh, because I did this sign.
Oh, okay. I see.
I carried this sign.
Okay. Right.
What is the temperature? Yeah.
Negative, negative 2666.
Oh, you know what? I screwed up. Maybe I had too many negative signs. Can you redo that? Because this natural log should come out negative. And so if this comes out negative, then negative times negative should give me a positive.
Positive 2,666.
2,666.
To the one decimal.
0.1 Kelvin.
Yeah.
Well, that's not heating up to 7,000 Kelvin, right? but we only get 1% reaction. 1% reaction, when you look at an equilibrium constant of 10 to the minus 4, an equilibrium constant of 10 to the minus 4 favors the reactants or favors the product?
Yeah.
Favors the reactants. So we aren't getting a spontaneous delta G because of this. And so we just have to heat it up to about 3,000 Kelvin to get it to partially react.
Are we comfortable when you work? Like, what are we comfortable with working? Like, hottest temperature wise?
This is still uncomfortable.
Yeah, right.
This is still very high temperature. You know, maybe like in a like a furnace, you know, like an electric furnace. You know what the highest temperature for electric furnace is, roughly?
Mine goes to like 455.
You have an electric furnace?
Or not electric, my oven.
Your oven?
That's a
For-
commercial oven.
is that Fahrenheit or is that?
No, it's in Fahrenheit.
That's in Fahrenheit. That's nothing. That's
It's the hottest I got.
yeah. That's about as high as you can get. That's pretty good.
Like chicken nuggets.
Well, like a platinum furnace will incinerate your chicken nuggets because a platinum furnace can get up to about 1,600 degrees C.
Okay.
It's almost 1,900 Kelvin. It's plenty to incinerate, but it's not hot enough to do this. So this is going to be a difficult temperature to achieve, but you know there's another error in here. Do you see an error in the calculation?
Yes.
Yeah. What is the error in the calculation?
The delta G naught.
Yes. This is the error here. This delta G naught is the value at 298. You know, is that valid?
No.
Or does delta G naught change significantly with temperature? It changes significantly with temperature, right? We're trying, and so we cannot use this. This is the error. We need the delta G naught at the temperature T, but we don't even know what the temperature T is, right? And therefore, is this possible to solve this equation?
Not accurately.
No. Unless, yeah, not accurate, but we can come out close if we do something else. Like we did with water. What did we do with water?
Didn't you solve the delta G node by assuming that delta, or making the assumption that delta H node and delta S node were not going to change significantly?
Yeah, that's exactly what we did. Rather than doing this, we know delta G changes significantly with temperature, but if we did this, where instead of using delta G, we use delta H minus T delta S, we come up with something like this. This is equal to delta H naught minus T delta S naught. So we get that divided by R ln of K. Now, in this case, what we're going to do is we're going to make the assumption that the value at 298 Kelvin is acceptable. Whereas here, we couldn't say the value of 298 Kelvin is acceptable because delta G changes significantly with temperature, but delta H and delta S do not. And so this will allow us to solve this problem. Otherwise, we can't because we need the delta H and the delta S at that specific temperature. So this could lead to a small error, but at least we can get somewhere with this. Now we got to solve for T, but you know this is not the easiest place to solve for T. And so I want to just back up and resolve this for T. That is, when we back up, we'll see that delta G is equal to delta G naught plus RT ln of Q. And then we're going to substitute it here. That is, what we want to do is we want to make delta G equal to 0. And therefore, delta G naught is equal to minus RT ln of K. And then substitute delta H minus T delta S under standard conditions is equal to minus RT ln of K. And then get both temperature terms on the same side. And so we get that delta H naught is equal to T delta S minus RT ln of K. And then factor out a T. And so this will give us delta S naught minus R ln of K. And then divide both sides by the parentheses term there. And then we get T is equal to delta H naught divided by delta S naught minus R ln of K. Officially, these are supposed to be at temperature T. The delta H naught should be at temperature T, delta S naught should be at temperature T, but we're trying to figure this out. The K should be at temperature T as well, which it is in this case. But we're going to make the assumption again that delta H naught at temperature T is about equal to delta H naught at 298 Kelvin. Delta S naught at temperature T is about equal to delta S naught at 298 Kelvin minus R ln of K at temperature T. K at temperature T is not a problem because we solved for it. And we know we want that K value at that specific temperature. And so let's plug in the numbers here. Delta H naught, delta S naught, K was what, 4.08 times 10 to the minus 4. And then recalculate the temperature. Did someone get it? Was delta H again? $180.5. All right, we'll do 180,500 joules. Delta S? 24.9 joules per Kelvin. R?
8.3145
joules per Kelvin. ln of K?
negative 7.
I'll just leave it as ln of K.
Negative 7.804.
$804
Yes.
times 10 to the
Negative 4. Wait, no. It says negative 7.8.
oh, that's right. It's power function. Is that right? And so what does the temperature come out to? That's still going to be a hard temperature to achieve. And just to get to 2010, we just have 1% reaction. It's not that much. Okay, let's do another example problem. This deals with the last section of this. That's with coupled reactions. I'll talk about this in a minute. But the reaction we're going to look at is this. Copper 2 oxide solid goes to copper metal plus 1/2 O2 gas. If I look at this, the delta G for this under standard conditions, look at this reaction. Tell me, if I were to reverse this reaction, do you recognize it? The reverse of this reaction is called well, it is a redox, but it also has another name. The reverse of this reaction is forming CuO from the element copper and the element oxygen. And so that type of reaction, forming a substance from the elements in their standard state, is called a formation reaction. And so when I look at this, I just see, oh, that's just the negative of delta G naught of formation for CuO solid. You see? We form 1 mole of substance from the elements in their standard state. Or we could use Hess's law. Hess's law would be that, delta G of the reaction is going to equal the delta G of formation of the products, copper and oxygen. Delta G of formation of copper should be 0. Delta G of formation of O2 should be 0. We're forming the element from the element, so copper would be formed from copper, O2 would be formed from O2, so there should be no change in energy. Minus delta G of formation of the reactant. Well, that's what we end up with here. 0 plus 0 minus this. Or you could just eyeball the reaction and see it. And so what is the delta G of formation for CuO? For CuO. A delta G. All right, so it's a minus 129.7 kilojoules per mole or kilojoules. It gives us a plus 129.7 kilojoules. What does that delta G tell you? Yeah, it's not spontaneous in the forward direction, highly non-spontaneous. Well, can we make it spontaneous? Tell me all the ways we might try to make this reaction spontaneous.
Increase the temperature, decrease the...
Yeah, we could try changing the temperature,
Decrease the pressure.
or we could try, going non-standard, or we could try a combination of the two. And so that's what we're going to do. Let's take a break, and then we'll do the calculations for this after the break. How long do you want? 10 minutes or 15 minutes? 15 minute break? All right. We'll take a 15-minute break. We'll start again at 3.